I'm not sure if it's an if and only if, but it looks like it. But I couldn't show it. So just a quick run through of how we did this. The main thing that we wanted to look at, the main quantity that we wanted to observe was actually this guy right here. AN to the R1 to the, what is it? This guy is what we wanted to look at. And it turns out that in all cases, in any of these cases, this quantity here remains bounded. It doesn't go off to infinity. It stays within some bound. Okay? So what we did was we took a root, one of the roots here. I think we take R1, right? Since R1 is a root of this polynomial, I get 0 is the sum from Ci of R1 to the minus I, from I going from 0 to k, right? Yeah. Did I write 1 to k? No, 0 to k. Sure. So R1 is a root, and I can multiply it by any number, and I multiply by this number here. And now, just playing games, I throw this guy in here, because it's just a constant, and I combine the exponents. So I actually have an R1 to the, and then to the 1 over m. See how these two things are exactly the same? But then I get cuter, and I throw in a minus an minus im plus an minus im to the 1 over m. From here, what was done here? Here I use the rational Newton's binomial theorem for rational exponents, and I again write this as the sum here from 0 to infinity of 1 over m choose j, and now an r1 to the minus im minus an minus im, and an minus im. This would be to the j, and this is to the 1 over m minus j. And I do more moving around, just some algebra and manipulation, and I end up being able to, from right here actually, what we want to do from right here is I want to plug in j is equal to 0 right here. If I plug in j is equal to 0, I get this goes away here, and I pull that term out. I get exactly a to the, I get this, and then plus this whole thing again, but starting from j is equal to 1. So, which is nice because this is what I'm looking for. This was what I was looking for. This is the guy that I want to show goes to 0. It's this guy. Right? So I have that 0 is this plus this. So if I can show that this goes to 0, then that means this must go to 0. Right? And to do that, we just played games with this. And it looks like this. really big. But it is what it is. Woo. Okay. How did I do this? What did I do here? I threw in an extra factor here of 1 over m, 1 plus m. And so this 1 plus m, because it's not dependent on j, I pulled it out right here. Right? I had this guy to the 1 plus m, I pulled him out of the sum. And then I had j to the minus 1 over m and 1 over m minus j, they're just dividing with the same exponent. You feel me? And when you divide it, you get this. I mean, imagine taking this and dividing it here. This gives me the 1, and then I have the an minus 1 over m down here. So this guy right here tells me that this limit right here goes to r1 to the 1 over m. I mean, it goes to whatever the difference is. It goes to r1 to whatever power, to the power of whatever the difference is between the indices. The indices here, the difference is 1 im. So this converges to r1 im times r1 minus im gives me 1. Minus 1 give me 0. So the limit of this guy right here is 0. And I actually showed in the paper, I had to do a little lemma, but basically I say that if any sequence bn goes to 0, then the sum from 1 to infinity of 1 over m of bn to the j minus 1 over m goes to 0 as well, for some large enough n. So the point is this whole thing goes to 0, because the limit of this goes to 0, and it's a sequence that's going to 0, then this guy will go to 0. That was just something that I had to prove aside. That indeed this whole thing goes to 0. And another thing that I had to prove, that I had to show aside, was the fact that, I already mentioned it, was that this is always bounded. It stays within a certain bound, which is this guy right here, except to the 1 over m, which doesn't make a difference for us. It's still bounded. So this is a sum where each term consists of some bounded term and another term that goes to 0, so that the whole sum goes to 0. And then that means that if this goes to 0, then this goes to 0, and that the property would be satisfied. And that concludes the presentation for today. Thank you guys for coming.